Hello, welcome to Modern Atomic Theory again, and today we are going to talk about quantum numbers. We mentioned those in another lesson, and you're probably very curious as to what they are. With all this talk about quantized energy and similar topics. So quantum numbers simply describe the orbitals of an electron. So there are 4 of them. They simply describe those orbitals, and the very first one is called the principal quantum number. It is sometimes represented as n, and it can be the number 1, 2, 3, 4, and continuing on up. It determines the energy state. So the principal quantum number, it's the very first one. It determines the energy state for that electron, and just try and remember that. The second quantum number, it's called azimuthal quantum number. You don't have to remember that number. It's kind of a strange number. It determines the shape. You can even refer to it as the shape quantum number. And it will always be represented by one of these numbers, S, P, D, or F. Each of those is a different special shape, and we have some representation of those over here. Here's an S. That's representing an s orbital and what that shape would look like. Right here, the combination of these 3 would be representing a p orbital, and these represent a d orbital, and these represent an f orbital. So those are the representations of shape, and we'll talk more about those in just a little bit. The third quantum number is the magnetic quantum number. Determines spatial orientation, and due to its complexity, we're not going to discuss that here, so you don't really need to worry about that one. The fourth and last quantum number is the spin quantum number, and it determines just what its title says, spin. It was discovered that electrons have an ability to spin one direction or another on their axis, and so the quantum number was named for that. We usually represent it with an arrow, like a little arrow up, or this little arrow down, a spin up, spin down. They're not actually spinning up or down, but that's just sort of the mark that we use to help and distinguish one from the other. It's important to remember that it takes all 4 quantum numbers to determine the state of an electron in an atom. So all 4 of these quantum numbers are critical in describing where that electron is in the atom and what it is doing. No 2 electrons can have the same 4 quantum numbers in the atom ever. That is an impossibility. That's a Pauli exclusion principle, really important concept that an orbital can hold a maximum of 2 electrons. And say an s orbital can hold 2 electrons in there, but they must have opposite spin. Say, for example, we have an electron occupying principal quantum number 1 and an s orbital. That would actually look like this, a 1s orbital. And that electron had a spin up, and another electron wanted to occupy the orbital. The exact same quantum numbers, 1s. It cannot have the exact same quantum number. It must then have the spin down. So atoms or electrons in the same orbital must have opposite spins, and there can only be 2 of them. So another important thing to notice is that this diagram shows 3 s orbitals, and they're a little bit different, obviously in size. This one is a 1s orbital. This is just simply an example of a 2s orbital, and here is a 3s orbital. And you can see that as the principal quantum number, the very first one, gets larger, the shell, the shape of the s orbital, gets farther and farther away from the nucleus. So that energy, as the energy goes up, that orbital gets farther away from the nucleus. So that's just something important to notice. As these numbers increase, those electrons will be farther from the nucleus because they will be higher in energy. So how many electrons can each shape orbital hold? So here we have our s orbital, nice little s-shaped orbital, and the number of sublevels that it just has 1. There's no other sublevels, it's just itself. So how many electrons would the s orbital be able to hold? Now I'll let you think about that for just a minute. And if your answer was 2, you are correct. It can hold 2 electrons. Now, if you take let's take the p orbital right here. It has 3 sublevels. How many electrons would those 3 sublevels be able to hold? Remember that each of those sublevels can hold 2 electrons. If you answered 6, you were correct. Here, get my little pen to work here. These are the electrons they can hold. And for the d orbitals, they have 5 sublevels, so obviously it could hold 10 electrons maximum. It can't hold any more. And for the f orbital, with 7 sublevels, it can hold 14 electrons. It's important to note that sublevels can hold 1 electron. That's perfectly fine. And a sublevel can be empty. That's perfectly fine. But it cannot have any more than the number right here. This would be the maximum number they'd be able to have. And also remember that each one of those sublevels, if they have 2 electrons occupying them, must have opposite spins. Just remember the Pauli exclusion principle. So here's a question for us. Does the shape of an orbital describe the movement of the electron? No, it absolutely does not. So the shape of an orbital simply indicates that the probability that the electron will be in that space. So here we have an s orbital showing, remember, our probability density clouds. The electron is much more likely to be in here, and as we go out and the color becomes less dense, there's less and less probability that the electron will exist in that space. And same with this p orbital. Here we draw the probability density clouds for a p orbital, and that's important to remember that these orbitals, these shape orbitals, have nothing to do with an electron path, or they aren't traveling around like this or something. It simply indicates the probability that the electron will be in that space. And one more thing, we had mentioned this before, that all atoms possess all orbitals, even if they aren't full. So here, let's say this is a hydrogen atom with its 1s orbital. It possesses all of the other orbitals. It has level 2 for principal quantum number. It has level 3, level 4, and it has p orbitals in there. Even if the electron isn't occupying them, those orbitals exist, so that if energy is absorbed by that electron in that atom, it will be able to move into those higher energy level orbitals and some of those other orbitals. So even if they aren't full, they're still there. Doesn't mean they don't exist. So that's it, and I hope you're able to watch this so that you'll be ready to do a fun activity in class to help us get ready to learn how to write electron configurations. So thanks, and we'll see you later.